Hello, my name is Yassine Haran, and I want to go over memorizing transformers, which is a method that was developed by a team of researchers at Google. The main motivation behind this method is that standard transformers have a short context window, and books or repositories of codes or proofs require a much longer context in order to answer questions. For example, characters in a novel may be multiple chapters uh, before that, or function definitions can be a significant amount of tokens before the actual use of those functions. And so what we need to do is to be able to retrieve that information from much before. Um, Also, another thing is that if we're only going to be learning information in the matrix weights, then it takes a long time to learn. But if we can be able to use context, then all the transformer needs to do is to memorize the information of the context instead of globally learning it in its matrix weights. The prior work that had been done on trying to increase the context window was the sliding window method or local attention, where we only can see a subset of tokens, and so distant tokens are still out of reach. So it still has a problem of not being able to look back to certain definitions that have been defined a long time ago. Also, there's the method of approximate or linear attention, where we basically approximate the attention or we compress all of the previous tokens into the current attention, and so we may lose details of previous definitions. Another method was the transformer XL method, where we keep a cache of the previous chunk. uh, However, the issue with that is we're only just doubling the receptive field, and so if there's any information from many tokens ago, we still lose that. And so most of these methods are also fully differentiable methods, so they're very expensive to scale as it takes quadratic time. The intuition behind how this method works is we look at it as in information retrieval problem. So we want to retrieve certain, for example, definitions from previous tokens. And what we do is we keep an external memory of all KV pairs that are generated from the context in a separate memory. And then when we're generating the current token, what we do is we do a k nearest neighbor search in order to find the k most relevant keys from the external memory. And then we do attention on those k keys along with the current context. And then we combine that memory attention along with our local dense attention in order to get results. The figure on the right is an overview of the architecture, and as we can see, it's similar to a regular transformer with the difference that we're just adding a k nearest neighbor lookup near the middle and then combining the attention from the retrieve k key value pairs along with the local context. And afterwards, we just add the local context k v pairs to the external memory. And the data split looks like the bottom figure, where for each document, we're splitting it up into a bunch of subsequences. Now, for the special layer for the kNN augmented attention section, what we need to do is we need to compute the queries from the current tokens in the local context. And then using that, we do local attention on those tokens. And then we also do a kNN search to find the k most similar queries from the external memory. And then we conduct attention on those as well. And then we combine both of these using a learned memory gate basically. So there's a scalar called BG, and that scalar determines how much information comes from local attention and how much information comes from the external memory. In order to improve results and speed things up, we use certain tricks in this method. For example, as I mentioned, we use a non-differentiable memory for the external memory, so there's no back propagation back to the key values pairs. However, this can create an issue called memory staleness, and that means when the weights are updating, but the keys and values were from previous weights. And in order to get rid of that staleness, what we can do is normalize the keys and the queries. Another thing that we do is we can use approximate kNN for retrieving the top k, and that's much faster. So here are the results of a comparison of perplexity between regular transformers and memorizing transformers. As we can see, the perplexity does decrease with model size as expected. However, when we're using memorizing transformers, the perplexity is also much less, and this is using a memory of 8K tokens. When training our memory transformer, we don't have to use basically training from scratch. What we can do is we can take a pre-trained LLM and just add the kNN memory and then fine-tune that. Or we can just train on a memory transformer that has a smaller memory, and during inference, we can increase memory size, and both of these methods do work. Finally, we want to talk about the qualitative behavior. So basically, what does the model actually extract when it looks back and finds the top K most similar keys? And so what we see is that actually it's exactly what we were expecting. So for example, if there's a function definition, it goes back and retrieves the definition of that function. Or if there's a lemma that's been defined before, it goes back and finds the definition of that lemma. And so basically, this is indeed a model that works as an information retrieval method. Thank you.